Welcome to this explainer brought to you by Forge College. Today, we are unfolding the engineering blueprint of block inclusion and execution finality. We've spent a lot of time recently looking at raw code and individual execution steps, but now we're looking at the grand finale. We're going to see exactly how those temporary computational steps actually get cemented into the Ethereum blockchain forever. It's this fascinating journey from a mere user intention to a permanent cryptographically secured reality.
Here is our schematic for today's lesson. We're going to cover 1. Back to Ethereum basics. 2. Entering the block. 3. The gas settlement process. 4. Reading the transaction receipt. 5. Building your local demo. And finally, 6. Achieving execution finality. We'll be breaking down the exact machinery of the EVM, tracking your transaction's journey from the chaotic mempool waiting room all the way to permanent block inclusion.
All right, Section 1. Back to Ethereum basics. First off, let's just acknowledge the absolute whiplash you might be feeling right now after our previous lesson. Switching contexts in Web3 can sometimes feel like trying to fluently speak two completely different languages at the exact same time. In our last session, we were speeding through using the Solana CLI to invoke on-chain programs. Well, it is officially time to put down our Solana wrenches and pick up our Ethereum compasses and protractors. We need to map out exactly how EVM execution translates into permanent state changes. This is a massive mental pivot. While Solana is all about parallel processing, where transactions can execute simultaneously if they don't touch the same state, Ethereum's EVM operates as a meticulous single-threaded state machine. Every single operation on Ethereum is precisely accounted for and must be strictly sequenced. State can be changed by anyone at any time, meaning we need absolute serial order.
Moving on to Section 2, entering the block. Let's start right on the factory floor, looking at how a transaction moves from ephemeral memory into the ledger's authoritative history.
Think of the mempool as this incredibly chaotic waiting room. Transactions are just piling up, essentially shouting to get noticed. But if you follow the intricacies of Web3, you know it's way more than just chaotic. It's a highly competitive dark forest. Here, block builders and validators play the role of the bouncer. They look at the crowd and determine the crucial order of transactions. They're extracting value, navigating front-running bots, and prioritizing users who are willing to pay a higher priority fee or tip. This intense three-step process is the gateway from temporary intent to permanent reality. Listen to this absolutely critical concept. Inclusion fixes ordering. This strict sequencing is vital for stateful contracts. For example, if you and I both try to buy the exact same limited edition NFT at the exact same time, the EVM doesn't just shrug and process us simultaneously. No way. The validator puts one of us first. This inclusion moment is when your transaction's execution outcome actually matters, because the state of the blockchain changes the millisecond the first transaction is processed, completely altering the reality for the second transaction.
Section 3. The gas settlement process. So, once you successfully make it past the bouncer and secure your spot in the block, it's time to head to the checkout line and pay the toll. Because remember, absolutely nothing in the EVM is free.
Gas settlement happens exactly at this moment of inclusion. It links the macro on-chain accounting directly back to those meticulous per opcode costs that you observed in your previous EVM execution traces. You've got your intrinsic base gas, which is just the standard 21,000 gas limit cost of doing business and sending the baseline payload. Then, stocked right on top of that, is the specific execution opcode gas. This scales up or down depending on how computationally complex your smart contract interaction actually was.
So, defining gas settlement. It's the moment your total execution cost is finalized and deducted. Every single drop of digital fuel you use to execute your code is tallied up here, contributing to the block's overall cumulative gas used. The network looks at exactly what you did, calculates the precise computational effort required to update the global state machine, and finalizes the deduction directly from your wallet balance. Which brings us to Section 4, reading the transaction receipt. Just like walking out of Costco with a massive cart full of bulk items, you are handed a literal receipt to prove exactly what happened during your transaction's execution.
Drawn out here like a technical ledger entry, these 4 fields are the machine-verifiable proof of your execution result. We have the status, unequivocally telling us if it worked or failed, the gas used, showing your specific fuel bill, the cumulative gas used, which is super fascinating because it shows how much total gas the block has consumed up to your specific transaction's exact position within that block. And finally, the logs, which are any events your smart contract emitted, almost like a receipt, itemizing exactly what you bought or changed. Keep in mind, an EVM REV opcode acts a lot like a dramatic abort mission button on a rocket launch, handing you a status 0. Your state changes are completely rolled back, meaning nothing you tried to do actually happened on-chain. But here is the catch, and it's kind of a harsh reality of smart contracts. You will still be charged for the gas you spent getting halfway to space before hitting the abort button. The decentralized network still had to expend the computational energy to figure out that your transaction failed, and they absolutely demand to be compensated for that work.
Section 5. Building your local demo. Let's step into the lab and run a local quality assurance test. Because, let's be honest, testing untested code live on mainnet is a very expensive way to learn. Instead, we're going to prove this machinery works exactly as described in a local sandbox without spending a single drop of real mainnet funds.
Using a local Hardhat node, you literally only need these 4 minimal files to create a robust transaction demonstration. We have a simple Solidity contract called counter.sol to increment a state variable, a script to send the transaction, a script to inspect the final results, and our local environment config. This tiny, elegant setup documents inclusion, gas accounting, and receipt status perfectly in a controlled environment, completely mimicking strict mainnet consensus rules right on your laptop.
Let's just follow these 3 simple steps to see how this works in practice. Step 1. Deploy your contract to the local node. Step 2. Run your send script to increment the count. Step 3. Run your inspection script. By following this flow, your script will force the local node to auto-mine the transaction. Because it's a local development environment, it instantly simulates a block builder pulling your transaction from the mempool and creating a block. This allows you to effortlessly pull the block's number and the transaction receipt immediately after broadcasting it. Now for the ultimate test of your understanding, the exact reconciliation. You need to verify that the gas used on your inspector script's receipt perfectly aligns with the raw execution trace from your previous EVM lessons. If you sum up the micro cost of every single opcode your contract executed, plus that intrinsic base transaction fee we discussed, it should exactly match the receipt's gas used field. Seriously, it is a beautiful moment of mathematical harmony when those numbers flawlessly align.
And finally, Section 6, Achieving Executionality. So we have our inclusion, our detailed gas settlement, and our official receipt. But what does this actually mean for the permanence of our data? Why go through all of this intricate cryptographic trouble?
This brings us to execution finality, the true holy grail of blockchain processing. It's the point where you can confidently reason that a state change is durable, safe to act upon, and written in stone. But think about this conceptually for a second. If a decentralized network has hundreds of thousands of independent nodes distributed all over the globe, how do we know they all definitively agree that your transaction actually happened exactly as you claim it did? Well, these 3 concrete principles provide the absolute evidence that execution took place under strict consensus rules. First, inclusion definitively locked in the exact order of events. Second, the gas settlement mathematically accounted for the network's computational effort. And third, the receipt status officially declared the canonical results of the world. Together, these intersecting elements effectively cement your state transition right into the chain's authoritative history. Once these are in place, the distributed network has agreed on exactly what happened and in what exact order.
But wait, what evidence must a validator individually reproduce to accept these state transitions? How do the rest of the nodes know the block builder didn't just make it all up? That is a very provocative question, and we are going to answer it in our next lesson on transaction validation rules, where we look at exactly how the rest of the network fact-checks the math. Until then, I highly encourage you to visit forge.college to dive deeper into this explainer and master other incredible Web3 concepts. Thanks for learning with Forge College, and I'll catch you in the next explainer.